The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so I feel I should have brought pizza instead of math problems. I mean, this is our final hour. Open for any questions, any discussion about Fourier topics, looking toward tomorrow evening's exam, and, well, hoping you'll find the whole course useful at many times in the future. So somebody emailed me that the posted solution, so I just posted a quick solution to the uncollected homework 10. And so I haven't even looked to see what did it say for this question, but what is the answer? If I convolve the delta function with the delta function, what do I get? Delta, right. If I convolve anything with delta, I get delta because I'm over in the other space, I'm multiplying by 1. Yeah, so if I use the convolution rule to go over to the other space where this becomes just 1 times 1, I'm getting 1, and that's the transform back, and I've got delta. So there, yeah. Well, that question won't be on tomorrow's exam, but I thought we could deal with that fast. Now I'm open to questions about any topic, homework or not. Yeah, thanks.
Could we go over one of the questions on the practice exam?
I could try. Did I make up the exam? Probably. Yeah, I'll recognize it. Okay. All right, I'll read it out. Oh, okay. Ooh. Okay. So this is an exam from 2005, not that far back. Okay, so it has some questions. Well, shall I tell you what the whole question is? But it looks like this part D is sort of separate from the others. But why not? This gives us some questions to think about. So if I just read out the questions. One was find the coefficients of the function is e to the minus x. That would naturally occur to me as a function that you could, so from 0 to 2 pi, and then periodic. Always good to graph it. So what will e to the minus x look like? It'll come down to, it'll much steeper than that, but that would do it. So that's e to the minus x. Here it's 1, and here it's e to the minus 2 pi. And then repeat. So find its Fourier coefficients. I'll just say what the question is, and you can ask me. And then what's the decay rate? Oh, maybe you can tell me the decay rate even before you tell me the coefficients. What would the decay rate be if I express this as a combination of Fourier terms, harmonics? How quickly will those coefficients drop off? So 1 over k only. That's right, 1 over k, because this function has a jump at 0, well, at 0 and again at 2 pi at every one of those points. It has a jump, I guess, of about this distance between 1 and that number would be the jump that we would see, of course, every time. Yeah, so the coefficients would decay like 1 over k. Then it asks to compute the sum of those coefficients squared. Okay, so how can we find the sum of those coefficients squared even before I know what they are? Well, you know the answer, right? How am I going to do this problem? Yeah, so I'm looking for the sum of squares of coefficients, and then there's this magic trick. What is it that helps me to find that sum of squares? How do I go about that? integral, I connect it to the integral of the function squared. It can go 0 to 2 pi of the function squared. And you remember the reason. And I've left a little space for the fudge factor. 2 pi or 1 over 2 pi. We can figure out what it is by taking a simple case. Yeah, why don't we take a simple case to figure out should there be a 2 pi or a 1 over 2 pi or what? What's a simple case here? Suppose I take f of x equal 1. Suppose I take the function f of x equal 1, then the right side, so if f of x is 1, the right side would be 2 pi, I guess, the integral of 1, and the left side would be what? What would be the Fourier coefficients of the constant function? Well, just C0, the only one we would have would be C0, the constant term, the C0 e to the 0, and it would be 1. So this, I'd have a 1 there when k is 0, and otherwise I wouldn't have anything. So this would be 1 squared, this would be a 1. So I do need to divide by 2 pi. Are you agreeing with that? That to make it correct, I better have a 1 over 2 pi to get that to be right. Okay, and then this gives me the answer then. I just do this integral e to the minus 2x, then f is e to the minus x. So f squared would be e to the minus 2x, which I can certainly integrate and get some expression. Yeah. Okay, so that's a straightforward part. And now to the part D, which you asked about, which is, oh, wow. Okay, so now I'm asking about an equation u du dx plus u of x equals train of deltas. So delta of x made periodic. Can I write it that way? So this is the periodic case. So I'm looking for a periodic answer. So I'm in the Fourier series world when I take the, I'll be looking for coefficients, not the integral transform here. Okay. So, right, so I'm making it periodic. So how do I proceed now with such a problem? So this is I mentioned this morning that, a problem like this could appear, so I'm happy to discuss it. What do I do? Transform. Absolutely. Take Fourier transforms. Okay, so what happens when I take Fourier transforms of u? Oh, I guess, so we're doing periodic, so we're going to go to coefficients, right? I'll call them, I think of u of x, shall I just call its coefficient c? It's the only function I have around, so I might as well use c so this will be, here's the function, and Fourier takes this to the set of coefficients. Okay, and the point is that we can separate, this is the whole reason why Fourier is so great, that we can separate, we can do each frequency separately. So let's see that. So this has coefficient ck, and what are the coefficients? What's the kth coefficient? So this is all the e to the ikx term. What's the kth coefficient of the derivative? ikck, right? And what's the kth coefficient of the delta function? 1, right? Is that right, or is it 1 over 2 pi or something? Is it 1 over 2 pi? Okay, 1 over 2 pi. Yeah, I guess that's right, because the coefficient, I would have to take the integral and that times, the integral with the delta function will give me the 1, and then there's a 1 over 2 pi. Right, okay. So now I've got the answer. Now I have this equation at each k, following each eigenvector, following each separate frequency. And it's easy to do. It's just 1 over 2 pi, and there's 1 plus ik, I think. Okay. And now, those are the ck's. So I've got I think maybe this is it. Sum from minus infinity to infinity. I know what the ck is. 2 pi 1 plus ik times e to the ikx. That's my u of x, I think. Had to be, right? So I just did the sort of automatic steps. I don't know whether I was, when I made up this exam, I don't know whether I was thinking I can find out what I can add. Can I actually do that sum to produce some function u of x that I am familiar with? I'm not sure. Anybody reading the question? So the question says, solve this differential equation. Doesn't say what it means by solve. Anyway, I've done it, I guess. Shall we agree that I passed on this question? Yeah. If we knew some tricky way to do this addition, but I don't immediately see it. So that's good. Okay for that one? Yeah, you're welcome. Thanks. Okay, so that was a very good question to ask because it got the method of the how do you deal with a differential equation. By the way, this could be a difference equation too. That could be u at x plus h minus u at x minus h. Shall I just emphasize that wouldn't have been any harder? U at x plus h minus u at x minus h over 2h. I mean, take, for example, plus u equals delta. This is like I've taken a center difference there for the instead of a derivative. How would you write a solution to that? Same method. Well, it's yeah. So what would the method be? I'd take transforms. So here, this would have coefficients ck. This would have coefficients 1 over 2 pi. And what would be the coefficients of these guys? Well, there's a 1 over 2h. So what are the Fourier coefficients of u of x plus h? Just to see that all these things, I've got constant coefficients here. Why shouldn't Fourier work? So if it's u of x plus h, how do I? So there's a e to the something factor, right? When I've shifted a function, then in the transform, I see an e to the I thing. So let's just see. If u of x, if u of x is the sum of ck e to the ikx, then u at x plus h would be the sum of ck e to the ik x plus h, right? No, nothing surprising there. So now I'm seeing the factor. There's ck. It's multiplied by the factor e to the ikh. So that's what. So this is the same ck, but an e to the ikh from that one. And this would be the minus, and this would be shift the other way, so it would be the same ck and probably e to the minus ikh, if I did that right. Yeah. Anyway, once again, we have a still linear problem. This is ck times something equals 1 over 2 pi. By the way, this thing is what I would call the transfer function. You see that language? We haven't used that language much. Or at all. It's a sort of more of a systems theory, control theory word. But hey, we're always doing the same correct thing. That's the thing that transfers the input to the output. So maybe the transfer function is 1 over. Maybe I include the division in the transfer function. So finally I get ck is this 1 over 2 pi guy divided by whatever that was, 1 over 2h times that number minus 1 over 2h of that plus 1, whatever is multiplying ck there. It's a transfer function. Yeah. So there's another word which could have and should have used before today, but here it is. Okay. So that's some thoughts about that question. Any other direction to go? Yes. Go ahead. Yeah.
I was asking about moving from U hat to U, like in problem 12.
Problem 12. Okay. 4.5 Fourier integrals. Number 12. Oh yeah, maybe that was also question was raised about was it right on the posted solution. So maybe not. Let's see what we want to do. Yeah, I just thought that was pretty. I can remember the day I thought of this equation. Integral of u minus derivative of u equal delta of x. I thought that's kind of a cool looking equation. But I don't know that I've ever solved it before. So integral of u. Actually, yeah, I look cheerful, but so I'm finishing the 4th edition of the linear algebra book, Introduction to Linear Algebra. So I love writing. I've done all the writing, and now comes the only horrible part, solving all those stupid exercises. So that, you may think of me in sunny Singapore or somewhere, but what I'll be doing is not on the beach. It's in an office somewhere doing problem 1.1.1 and 2, 3. It's just, it's not life. I mean, but okay. Anyway, that looks like a pretty good equation, and certainly I'm going to transform it. Yeah, so I can see a little question coming up. So am I in the Fourier integral world? Yeah, so I should use this notation. U hat of k, right? Over ik, is that the right thing when I've integrated? Yeah, that's made it smoother. That's dragging the function down. And I guess the one point that's a little tricky there is always, are you dividing by 0? So because 0 is one of the frequencies, and so I sort of need u hat of 0 to be 0 for this. So it's looking slightly dangerous at k equals 0, but otherwise it's certainly improving things by speeding up the decay rate. And then this would be minus ik u hat of k, as we just said. And this would be the 1. Maybe it's a 1 in the Fourier integral world where the 2 pi went in a different point. So I think that's, yeah. So I would now just, the usual thing, what's the transfer function? 1 over ik minus ik. So that's my transfer function that's multiplying u hat. Maybe I can simplify that by putting it all over ik, 1 minus ik. Is it plus k? Does that look good? Or does that look bad? K squared? Does that look better? So I'm wondering, is k, so over here, is k squared over ik, is that the same as the minus ik? Yeah, yeah. Bring it up, and the minus I squared is 1, and I've got k squared. Yeah, so this looks good. So that's then dividing by it gives me, because I'm dividing the 1, so u hat of k is 1 over this. So it's the transfer function 1 plus k squared. Okay. I don't know whether I had in mind to go any further than this. Did you get this far, or what? Yes. Yeah.
It said then find u of x.
It said that? Oh, jeez. That's what I bitterly regret saying these things. Yeah, okay. I don't know u of x. Did anybody have any luck? You do. Did I say it was the derivative? 1 over 1 plus k squared. Oh, yeah. Right. 1 over 1 plus k squared, we know what to do. And then ik will take its derivative. Huh. So what do we do if it's 1 over 1 plus k squared? That's the one where that was the guy which was the e to the minus x, right? Oh, it's just one side? No, two sides, isn't it? Two sides, yeah. Yeah, we just got a corner. Yeah, okay, that's looking good. Now that maybe I need to divide by 2. A is 1 here, but there is a division by 2. Yeah, that looks good. Okay, and now I take, right, this function, its transform has that, and now if I want to multiply it by ik, I have to take the derivative. So I believe, with your help here, that the derivative of that is the same. So can I just take the derivative while we're looking at it? I mean, e to the x is the most, that was created to take its derivative, right? So its derivative is itself. The derivative of this is a minus. So I think that maybe that's the answer. E to the x over 2 coming up to 1/2, I guess, and then well, the picture won't look because of that minus sign. Yeah, good. Because that minus sign, it's minus e to the minus x over 2. So it starts at minus 1/2. So there's a jump of 1, or a drop of 1. Is that right? There should be a drop of 1 in u hat? Probably. Yeah. The integral will be smooth at 0, where the delta function's hitting us. I have a minus sign and a derivative. Yeah, doesn't that look good? Drop of if the derivative has a delta, the function has a jump. And with that minus sign and with 1 delta, the jump should be a drop of 1, which is that. Yeah. And the integral minus the derivative should be otherwise 0. Yeah, so this is, again, this is not unrelated to exam question. I did all this stuff, and I really should check, did I get it right? Does that solve the differential equation? I mean, you could say, of course it does if you took all these steps right, but it's wise to check. Plug it in. Okay, it has the drop of 1, so it deals correctly with the delta, because the derivative has a delta, and things match. And now what else do I have to check? I have to check out all the other points, right? I just checked that, yep, this answer is good at the jump, the tricky point, but now what about all the other points? So where the delta is 0, I should just check that the integral of u, so what is the integral of u? Let me just check for the points left of the origin. So I'm just going to look at this part. X negative. So it's integral, what's the integral of e to the x over 2? I guess e to the x over 2, right? Minus, and what's the derivative of e to the x? Oh yeah, the derivative is also e to the x over 2, and I get 0 for x negative, as I want to, because the delta is 0 in that left side. And similarly on the right side it should be okay, and then the key point was that the jump was right. Yeah, so thank you. I'm glad you asked about it. Yes, please. What, sorry? Why did I take the derivative? What will be the derivative of this? Yes, there is. That's right. What would be the derivative of this? Yeah, good question. What's the derivative of this answer? So it's that on the left, and then there's a delta function, a minus delta, right? Because it's dropped down. And then the derivative of that is e to the minus x. Yeah, so if I graph the derivative, cool. If I graph the derivative, it looks like the function. It has a spike going down there, at the origin, and then the derivative here is positive, right? Because its function's coming up. It's e to the minus x over 2. It's positive. It's there. Yeah. Oh, wow. That's a nice graph. So that's the derivative. This is a graph of du dx. Yeah, thanks. And similarly, I could graph the integral. The integral, well, would you want to see the integral? Probably not. Maybe, yeah. I don't know. The integral will probably look pretty much just like that, but without the delta. Yeah. Huh. Cool. Isn't that nice? Yeah. I mean, it's artistic. That's the derivative, and the integral is the same thing without the delta, and when you subtract, you get the delta. Okay. You sure you guys don't want to come to Singapore and help with these problem solutions? There's plenty for everybody. Okay. No. All right. So what, another question. Yeah.
All right, back to the 2005 test.
2005. Okay.
I can give it to you.
All right. Yeah. Which one?
I somehow didn't set up the part B.
Which?
correctly.
Okay. I'll just read out the whole question. Yeah. So this is 2005, problem 3. Okay, it's a half-hat function. Oh. This is Fourier integral because it's on the whole line, and it's half a hat for between 0 and 1. The function is coming down, and then otherwise it's 0. Draw its graph. Done. Graph its derivative. Okay, let's graph the derivative of that function. Derivative is certainly 0 along there. Then the derivative is minus 1 here, and then the derivative is 0. So the derivative looks to me like it's that. Okay, so it has a, yeah, that function. Is that right? No, it's not right. There's a delta. That was the tricky part of the problem, right? There's a delta in the derivative right here because of that jump. There's a delta. Okay, great. Yeah, now, is that better? Yeah, thanks. That's good. Okay. What's its transform? The transform of this derivative. What's the Fourier transform? Well, I guess we got two parts. So this is my function u prime of x, the derivative. Now what's u prime transform? So it should be a function of k now. All right, what do you think? So it's the sum of two things, that delta, which Fourier transforms to 1, and this guy down below between 0 and 1, which is like the one we did today. We've got the integral from 0 to 1. Now it happens to be a minus 1 e to the minus I kx dx, right? And that, of course, we can do. Yep. Okay. Oh, there's solutions here. Yeah. Right. Yeah. So, okay. So I think we're doing all right. This expression is familiar. It's 1 minus e to the minus ik over the ik. Isn't that right? We have a is the minus? Yeah, I think the minus looks good. Yep. And yeah, at least that's here, and it's probably got the minus signs correct. So why was it? I plugged in x equal 1, and that's why I got an e to the minus ik. And then I plugged in x equals 0, and that's where that 1 came from. Okay, so, but your question was about parts? That was it. That was it? Oh, I see. Okay. Okay, yeah. All right, right. And then the next part asked about the transform of the original guy. The transform of the original guy. Now, what would be the transform of the original guy? The original u. Yeah. Yeah. Right. Okay. Yeah. I'm just, the reason I'm sort of stuttering is that if I'm going to integrate, I mean, what are you going to tell me how to, what's the quick way to find the transform of the original u now? Divide by ik. Right. Divide by ik. And then I'm all ready to do that, except I'm worried at k equals 0. But it should come out all right. Now, so I have to hope that this thing comes out to be 0 at k equals 0. Can you see that it does? What is, yeah, this is a good point. What does u hat at 0 represent? Have you thought about that? What, if I look at the Fourier transform, which I've got here, so let me write what I've got here. I've got here the Fourier transform of this function. And if I take the Fourier transform of any function and I look at 0 frequency, what am I seeing? The average, right. I'm seeing the average. What's the average value of that function? We never thought about that, but that's fun. What's the average of this guy? If I integrate over the whole line, do I get 0? Yes, because I get the integral of the delta part gives me a 1, but the integral of this box part gives me a -1. So the integral, this does equal 0 at k equals 0, and I can safely do that division and get, so now u hat of k is this expression divided by ik. So it's 1 minus this thing, I'm just copying, minus ik over ik, all that divided by ik. And I can, of course, maneuver that some more to make it look better. Yeah, yeah. Okay, these are good questions because it's giving me a few functions to do the standard rules: shifting, integrating, dividing, differentiating. Yes. Oh, here's a Christmas present. What does that mean? Is the convolution of this function with itself the whole hat? Oh. Why is that a Christmas present? Is the convolution of that with itself? So first point, we don't want to compute a convolution. You may have noticed, you have not computed convolutions of things like this. It's not a lot of fun because you have that integral to do, and you'd have to separate out the parts where it's this and the part where it's this and the parts where it's that. It's not nice. Much better to multiply in the transform domain. Much better. Okay, so if I multiply in the transform domain, I don't think I get the Fourier transform of the hat, of the whole hat. But can you give me a convincing argument why, if here I'm in the transform domain and I'm going to convolve with itself, so I'm just going to square it.
So the decay rate would be k squared.
Would the decay rate, what's the decay rate as it is now? The decay rate is, yes, that's the decay rate is a good key. So what is the decay rate right now? Here's a function with a jump. So I know that even though it has a slightly messy looking transform, I know the decay rate. It's what? With a jump is 1 over k. Okay, so this must be, and I sort of do see a k down here, so that's sensible. Okay, now if I convolve, then I multiply in this domain, so that would give me the k squared, as you said. So could that be the transform of the whole hat? Does the whole hat have a, ooh, could be. I'm pretty sure the answer is no here. Yeah, no way. Yeah, I think that's the best answer. Yeah. Yeah, I've lost the reason because I'm getting a k-squared decay rate. If I convolve something with itself, that would give me a k-squared, and the decay rate of for the transform of the hat is a k-squared, but they wouldn't be the same. Yeah. Okay. Yeah, I won't. Yes, please.
I'm confused. It seemed like in that problem when you transformed the delta function you had 1, and in the earlier problem it was 1 over 2 pi.
Right.
What was the difference?
It's just convention. The difference was that was the Fourier integral problem, where we put, you might have noticed that the 2 pi goes on the other, and this was the Fourier series problem. That was the only difference. So it's just the convention. And maybe other people would choose a different convention. Yeah, yeah. So that is a slight wiggle in the presentation, that the 2 pi in the Fourier integral section got moved to the other, to the transform in the other direction. Yeah, yeah. Good. Yes, thanks.
I'm a little confused about how you're finding the decay rates.
Oh, okay. Just, I'm really just going by this rule that if there's a jump in the function, then, and nothing worse, then the decay rate is 1 over k. And if there's a jump in the derivative, as there would be here, so that has a jump in slope, then the decay rate is 1 over k squared, and so on. But those are the main cases. Yeah, so I'm not using anything deep there. By the way, I'm realizing that one MATLAB problem that I didn't assign this semester, but it's quite fun, is to actually see the Gibbs phenomenon. It's we know the terms in the Fourier series with a jump, and if you computed, make it the periodic case. If you computed the terms in the Fourier series, they would stay near here, and then they would. But then I'd see the famous Gibbs stuff here. So that, it's quite pleasant to see the printout of the Gibbs phenomenon as you not getting any shorter, just moving closer to the jump as you increase the number of terms. Yeah, it's quite interesting. But couldn't do everything. Yeah, ready for more. Any questions from? Well, these are good. Yeah. Yeah. Anything else? Yes, thanks. Sorry.
Did you do a problem with cyclic convolution?
With cyclic convolution. Okay. Yes. Well, what could I do with cyclic convolution? Yeah. Let's see. What should I do with cyclic convolution? I better make a little space anyway. Okay. Let's see. All right. Let me make a little space and think. Anybody got a suggested problem for cyclic convolution? I mean, one type of problem would certainly be if I gave you if I gave you a cyclic convolution and asked for the direct way would be to say, okay, what's the cyclic convolution of 1, 4, 2 cyclically with 2, 1, 3 or something? But that's just a calculation, so you would get that. I won't discuss that further. Now suppose I ask it with the unknown, the thing that I don't know here. So let me do that. So shall I say 3, 1, 1, cyclically convolved with some unknown x0, x1, x2 equals some right-hand side. What shall we take for the right-hand side? 1, 1, 1, for example. Okay, there's a, yeah, just, I'll erase the top one because that's not. Okay, how would you go with that one? So that's 3 by 3, 3 unknowns. It's linear, so somehow I could write that as 3 equations in 3 unknowns. The question is, how do I get some insight into this? And when I'm seeing a convolution, what's my immediate thought? Transform. That's what this month is all about. November and these days is all about it. Transform. So so I'll take the DFT of everything. So what's the discrete Fourier transform of 1, 1, 1? So I'm just, up there is going to be the transform, so let me call it x0 hat, x1 hat, x2 hat, just to emphasize. So n is 3 here in this problem. Or you maybe C0, C1, C2, you might prefer, whatever. And now this is going to be a multiplication. So it's, in MATLAB notation, it'll be a dot star, right? And so now I have to, these are the known ones. So what's the discrete Fourier transform of 1, 1, 1, the cyclic convolution of that? It's 1, 0, 0, is it? Or 3, 0, 0? Is it 3? I guess when I ask the question, you're open to 2 answers. You could either be going from X space to frequency space or frequency to the other, because I haven't told you what space we're in. But let's go with that one. So that, how did you get to there? Yeah. Right, you multiplied by the 3 by 3 Fourier matrix. Is that what you did? All right, so now can you do that here? I got to, so separately I have to do a little multiplication of the 3 by 3 Fourier matrix, 1, 1, sorry, let me get it right. So I'm going to transform this. Okay, maybe make a little space here. Transform that. So it's 1, 1, 1, 1, 1, and this is w squared, and w to the 4th, which is the same as w. Okay, and now I want to multiply that by 3, 1, 1, and get the answer there. Okay, so what do I have? 5. And what is that other one? Oh boy, what is 3 plus w squared? Anybody know that one? Well, I do know what 1 plus w squared is. It is 0. Why is 1 plus w squared 0? So I claim that if I have 3 plus, I think the answer there is 2. And here I think I also have 3 w squared. I think if it was a 1, the answer would be a 0, but it's a 3, so I still have 2 there. I think that's probably right. Can I just remind you why? There's 1, there's w, and there's w squared, and they add to 0. Yeah, because if you, for many reasons, that's a very, very handy property that the sum of the nth roots of 1 add to 0. Okay, so now where am I? So I got 5, 2, 2. So I've transformed. Now what do I do next? I divide. So now I can, so this is telling me that 5x, this is 3 separate equations. It's 3, 2, x1 hat is 0, right? No, x2 hat, and 2, x2 hat. Sorry, 1 was right. And 2, x2 hat is 0. I'm just doing the multiplication as I'm supposed to. In the other space, it's for each component separately. So now I know x0 hat is 3/5 and the others are 0. So now I know what these numbers are. Oh, yeah. 3/5, 0, 0. And now what? I mean, that's clear. That statement's clearly true, right? Point star means 5 times this gives me 3, 2 times 0 gives me 0, 2 times 0 gives 0. So I'm golden, but I'm not finished. So that's not x. That's its transform. So what do I have to do? Go back. Okay, so so now can you tell me what this is? Up to a factor of 1 over n or n, which we may have to figure out separately. But so apart from this possibly appearing and probably appearing, what would be the, give me an idea of what's the inverse transform of that thing? 3/5, 3/5, 3/5. Good. 3/5 all 3 times. Okay. And now I can check to see if it's right. And again, I've skipped. I have not attempted to get the 1 over n's right. I've just waited to the end. So now I'll just do this convolution and see if I really do get 1, 1, 1. So can we do that convolution? What is a typical, say this guy? Where does that come from in the convolution? It comes from this times what? This. That's the constant, right? And that's the constant, contributes to the constant. And what other products contribute to the constant? So we're really seeing, thank you for this question. We're really seeing, so this one multiplies which one? Right? I'm thinking about, remember, the answer is this one multiplies this guy. You may say, don't worry me about it because they're the same, but it's nice to know. So this one multiplies this one, and this guy multiplies this guy, and we'll remember in a minute why, and then you add them up. That's what convolution is. So I'm getting 9/5 plus 3/5 plus 3/5 is 15/5, so that's 3. So what's your conclusion here? I should divide by 3, right. So I should divide by 3, so that's easy to do. Those will all be 1. Yeah, okay. So that's the right, that's the right answer, right? And then I check that it's right. Yeah. Yeah, so let me just close by remembering why was it, well, so that was, I'm doing just a forward convolution here. Solving the equation was a deconvolution, figuring out that x. But now that I've got it and I'm just checking, that's just do it forward and see if you got the right answer. And so we're just remembering how to, what it means to do a convolution. So you remember the point about convolutions, that if I'm convolving ABC cyclically with DEF, that the constant term, just tell me again now, what's the constant term in this? It's AD plus B times what? This is the first term in the convolution. You remember that, the day we brought convolutions into the course? What does B multiply? F. Why F? Because B is the coefficient of W in the, if I'm thinking polynomials, this is A plus BW plus CW squared, and this corresponds to D plus EW plus FW squared, and I'm looking for the constant. So I get an A times a D gives me a constant. BW times what? Times FW squared gives me the W cubed, which is the 1. So the BF here, and then there's a CE, because CW squared multiplying EW gives me the w cubed, the 1, which folds in. Yeah, okay. So anyway, that's a quick reminder of cyclic convolutions. That was a good question to ask. Yeah. You know, I fully realize this, especially this third topic, lots of things like this. Straightforward if you have lots of time, but we had to keep moving. This, remembering what cyclic convolution was, is a good chance to do it.